All right, so I'm going to go through everything for AP Physics C mechanics. This is straight from the College Board. I believe this is all open and available to you, so I shouldn't be breaking any rules. If this video goes away, then obviously I did, so sorry about that. All right, let's start off with Unit 1. Unit 1 is going to be 10 to 15% of the exam, which is great news because my students typically are very strong with kinematics. Looking at our learning objectives on the side, you can read those and see what you should be learning. But what I'm going to focus on and what I'm going to read to you throughout this video series is the essential knowledge, the stuff that College Board says you need to know in order to do well on this exam. Which sounds to me like it's the important stuff. So, onward. Let's get to it. First of all, scalars are quantities described by magnitude only. Vectors are quantities described by magnitude and direction. Oh yeah. I underline this magnitude because I want you to think, whenever you see this phrase, absolute value. That absolute value means we don't care about that negative. That indicates our direction for scalar quantities. Vectors can be visually modeled as arrows with appropriate direction and lengths proportional to their magnitude. So if there I have vector A, that's what it looks like. Distance and speed are examples of scalar quantities, while position, displacement, velocity, and acceleration are examples of vector quantities. It is important to know your vector quantities versus your scalar quantities because you should know if you need to account for direction, momentum, force, all that other stuff that's going to come later. Vectors can be expressed in unit vector notation or as magnitude and direction. So you might see the same old vectors that we saw in AP Physics 1, or you might see it in this scary looking manner. All this says is we have A I hat plus B J hat plus C K hat. We're using I hat, J hat, and K hat for X, Y, and Z. You can memorize that because both of them are alphabetical. The way we handle I hat, J hat, and K hat is depending on what we're doing with our two vectors. Let's say we're adding two vectors. We're going to add the I hat to the I hat. And that will give us our resultant I hat. And then we can take vector A J hat plus vector B's J hat. And that's going to give me my resultant J hat. And then same thing for K hat, and so on. And your final answer is going to look like this, where it's R I hat plus R J hat plus R K hat. And you could just leave it like that. The position vector of a point is given by R. So this is our position vector. And the unit vector in the direction of the position vector is denoted R hat. So R hat is going to give me the direction, whereas my position vector is just R. A resultant vector is the vector sum of the added vectors components. That's what I just said up there. In a given one-dimensional coordinate system, opposite directions are denoted by opposite signs. When you start a problem, you should already have in your mind what direction is positive and what direction is negative. Typically, we're going to take right to be positive, left to be negative, up positive, down negative. But sometimes you're going to find yourself saying stuff that makes it go, that's down. So down is our positive direction. And therefore our air resistance is in the opposite direction. Remember back from, pre-algebra, the negative sign just means opposite. When using the object model, the shape, size, and internal configuration are ignored. This is what we do when we have a car and we analyze that car going some distance. Well, are we talking about the front of the car or the back of the car? No, we're shrinking the car down to this tiny little point, which is the center of mass, and we're tracking that motion. Displacement is the change in an object's position. Delta x is displacement, whereas x is distance. Could be position. Final minus initial. That's what delta is. Averages of velocity and acceleration are calculated considering the initial and final states of an object over an interval of time. So if your initial velocity is 5 and your final velocity is 10, the average velocity could be between those two. So it could be 7.5. For it to be 7.5, we're assuming that those two velocities are happening for the same amount of time, which may or may not be true. Average velocity is the displacement of an object divided by the interval of time that displacement occurs. Sometimes I see people write v equals x over t. No, that is not the case. It is the average velocity. And it's important to note that it's the average velocity, so that way you don't try to say, oh, this is the final velocity or the initial velocity. No, that is just your average velocity. Average acceleration, same kind of idea, same looking formula, delta v over delta t. An object is accelerating if either the magnitude and or direction of the object's velocity are changing. We saw that when we have an object with a velocity in this direction, but a constant speed, yet there is an acceleration acting towards the center, which later on we called a centripetal acceleration, that is going to change the direction. So because there is a change in direction, we have acceleration happening. Also happens when objects speed up or slow down. If our acceleration is to the right and velocity is to the right, we're speeding up. If acceleration is in the opposite direction of velocity, we're slowing down. Calculating average velocity or average acceleration over a very small time interval yields a value that is very close to the instantaneous velocity or instantaneous acceleration. To find our instantaneous velocity or instantaneous acceleration, let's say we have velocity versus time and we're trying to find our instantaneous acceleration. You already know what we're going to do. We're going to take the slope of that tangent line. Or we could just say a equals dv dt. And that'll give us our instantaneous acceleration, or velocity equals dx dt, instantaneous velocity. As the time interval used to calculate the average value of a quantity approaches 0, the average value of that quantity approaches the value of the quantity at that instant, called the instantaneous value, like the instantaneous acceleration or velocity. Instantaneous acceleration, just talked about. Time-dependent functions and instantaneous values of position, velocity, and acceleration can be determined using differentiation and integration. So for this, we should, after a year in physics and a year in calculus, we should have this down, though apparently I don't. X to v, v to a, we're going to take the derivative. And then to go back up, we're going to take the integral. That's what that means. So to get velocity, velocity is integrating a dt. Motion can be represented by motion diagrams, figures, graphs, equations, and narrative descriptions for constant, motion diagrams. Don't forget about those. So we have dots. In this case, the spacing is increasing as I go from left to right. But if I say my velocity is to the left, am I speeding up or slowing down? Or what direction is my acceleration? My acceleration will be to the right because we're slowing down. So acceleration must be in the opposite direction. Those are our motion diagrams. These are the strobe lights happening at equal intervals. So in between 1 and 2, this is 1 second. In between here and here, this is the second, third second, so on. These three equations are called a constant acceleration constant acceleration equations. Sorry, I'm going to do this very informally in one take, just because time, right? These can be used to describe instantaneous linear motion in one dimension. So, it's not entirely important for you to memorize all of these equations, but you should have an idea what they look like. I also recommend naming them, so that way you can reference them quickly. Here we can call this the no displacement equation. This is our no time equation. There's our no time equation. And then this one is just called displacement, because it gives us displacement. Okay, so if you have those memorized, the names of them memorized, and kind of what they look like, you can look at your equation sheet and say, oh, there's the no time one. It's Vf squared equals V naught squared. I almost forgot that, but I didn't. The equations are written to indicate motion in the x direction, but you can use these in any single dimension as appropriate. So we can use these in the z direction if we wanted. We can use them in the y direction. In fact, all of these equations can be transformed to the y direction. Minus gt if we're going to take down to be negative, or plus gt if we take down to be positive, whichever one works for you. There should be a negative in there somewhere, probably. And you can do that for all of them. That sub x is there only to remind you that this can be done in the x direction or y direction or z direction, but I don't think we have to worry about that. Near the surface of the Earth, the vertical acceleration is going to be 10 meters per second squared. Don't use 9.81. It's a time test. And let's keep those calculator strokes down. Graphs of position, velocity, and acceleration as function of time can be used to find the relationship of these quantities. So you should have an idea of your common relationships. So that would be like a square root relationship, y proportional to square root x, exponential increase, x squared, linear, y equals x, those things. An object's instantaneous velocity is the rate of change. I feel like we've done that already, right? Which is equal to the slope of a tangent line. Yeah, we definitely did. An object's yeah, we definitely did that. Instantaneous acceleration is the slope of a line tangent to on a velocity versus time graph. One more time, our tangent line, and we're going to take the slope of that, and that is going to be the change in v over the change in t. Here to here is my change in t. Here to here is my change in v, which is on my y-axis. When that change becomes really small, we start talking about the differential velocity and the differential time. That d in front of any variable means differential, infinitesimally small. The displacement of an object during a time interval is equal to the area under the curve of a graph of the object's velocity as a function of time. Before we get into that nice integral, let's talk for a second. Let's go back to that average velocity equals delta x over delta t. Because I'm dividing these two quantities, that means this is going to be a slope. So this means my slope, and this means rise, and this means run. So if I were to plot an x versus t, x on my y-axis, t on my x-axis, whatever that slope turns out to be is going to be my velocity. If I go to my average acceleration, and I have delta v over delta t, that would be the same thing, right? I can do v versus t graph. The slope is going to give me acceleration. But what if I multiply by delta t to each side? Now I have delta v equals a average times delta t. So now I have two quantities being multiplied. When I have two quantities being multiplied, I can plot these two, my a average and versus my t, and this is just like length times width. So whatever that area between my curve and the positive x-axis is going to give me my velocity, and that is what our integral tells us. So here you can see we're integrating. I really want to tell you to always have definite integrals, just because it's going to make your life easier. And what that does is that, number one, we don't have to worry about that plus c. Number two, at least in mechanics, for E and M, there are times where we'll take an indefinite. Number two is it's going to remind us that we need to set our bounds. Sometimes you're going to see a point for having correct bounds and attempting to integrate, or something like that on your FRQs. So we want to set our bounds to the times that we care about. Remember, this is our final time and this is our initial time. We're going to integrate that, and that's whatever we get. We're going to do final minus the initial. I know, you're in calculus. You know how to, not everybody. The change in velocity, we're integrating a with respect to time, as we just said. I've got a boundary statement here. AP Physics C Mechanics and AP Physics C Electricity and Magnetism expects that all situations G equals 10 will be used. However, you're not going to be penalized if you use 9.8, 9.81. It's all about calculator strokes and saving those microseconds, because those microseconds add up to seconds. Onward. Reference frames. The choice of a reference frame will determine the direction and magnitude of quantities measured by an observer in that reference frame. So if we're given a situation where a car is driving from point A to point B, here's A, here's B, we should note what direction is positive. That's our reference frame. That's what it's saying. Now I know that I'm going up, so I'm going in the positive Y and the negative X direction to get to B. Measurements from a given reference frame may be converted to measurements from another reference frame. This is leading up to our equation, I think. Oh, right, we don't get the equation. This is a memorized equation. So that is our apparent velocity equals the velocity of the object plus the velocity of our frame of reference. And you can use that to bounce between the frames of reference, either for the object, where things in an inertial frame of reference are not accelerating, or from the side of the road, watching the car drive by. The observed velocity of an object results from the combination of the object's velocity and the velocity of the observer's frame of reference. Combining the motion of an object and the motion of an observer in a given reference frame involves the addition or subtraction of vectors. These are vector quantities, so maybe this is going to the negative. So this is going to be adding a negative here, if that's the case. Just remember, use your vectors. Vectors mean direction. Combining the motion of an object and the motion of an observer in a given reference frame involves the addition or subtraction of... Yeah, I just read that. Sorry. The acceleration of any object is the same as measured from all inertial reference frames. Unless otherwise stated, the frame of reference for any problem is assumed to be inertial. So we don't have to worry about a centrifugal force, for example, where you would be in an accelerated reference frame and describing the forces that are happening. Describe the motion of an object moving in two or three dimensions. Motion in 2 or 3 dimensions can be analyzed using one-dimensional kinematic relationships if the motion is separated into components. What this means is keep your x, y, z separate from each other. Don't try using this equation, x equals 1/2 gt squared. No, we can't do that because that's using the acceleration in the y direction for a horizontal displacement. If we needed to use both of these, like with projectile motion, we would use x equals 1/2 ax t squared, assuming initial velocity is 0. In the y direction, actually, probably what we're going to do is we're going to do bx times t. And then in the y direction, we're going to use y equals 1/2 gt squared, assuming drop from rest. And maybe we need to solve for the time here, square root of 2y over g. And we take that time and we plug it in there because time is going to be the same in all 3 directions. Velocity and acceleration, though, may be different in each dimension and may be non-uniform. What does non-uniform acceleration look like? It's going to look like this. Anytime you have a changing quantity, use the math of change. Calculus. Motion in one dimension may be changed without causing a change in perpendicular. In a perpendicular dimension. Okay. So an object can be moving through the y-axis or through the y dimension and not affect things happening in the z direction. That's fine. Projectile motion is a special case of two-dimensional motion that has 0 acceleration in one dimension and constant non-zero acceleration in the second dimension. Acceleration due to gravity or our gravitational field. 10 meters per second every second is how much our velocity is changing every second. AP Physics C Mechanics only expects students to quantitatively analyze the motion of an object in 2 dimensions. AP Physics C Electricity and Magnetism expects students to also qualitatively describe the motion of a particle in 3 dimensions. So mechanics, we're only dealing with 2 dimensions. E&M, you know,